In this video, we're going to talk about section 4.2, which is the greatest common factor and least common multiple. So we're going to take this in turns. We're going to start with the greatest common factor, but they do have some ideas in common. So we're going to kind of look at that. Let's define what a factor is really quick. So a factor is a number that when multiplied by another produces the given number. Okay, and you've probably heard the word factor before in math. That's not like a foreign word, but like, let me give you an example. If I told you to factor the number 12, factor 12. So according to the definition, I'm looking for a number that multiplies to be 12 when it's multiplied by another. So a factor of 12, or to factor 12, another way of saying that is to rewrite it as a multiplication. Okay, so if I want to rewrite 12 as a multiplication, there's a few ways I could do that. I could say, okay, well, 12 is 2 times 6. Or I could have said 12 is 3 times 4. All right. There's a few different ways I could have done that. I could also approach it as listing all possible factors of 12. And here I'm going to write that as a separate example. List the factors of 12. So now I'm looking for numbers all the numbers that multiply to be 12. List the factors of 12. Wow. I don't know why I'm having such a hard time writing that, but whatever. Okay, eventually I'll get there. All right, so based on what I already have written, I just realized I wrote the multiplications, one with a dot and one with an X. I don't know why I did that. Okay, there we go. X. I have 2 and 6, 3 and 4. Those are all factors of 12, but there is another set of factors of 12 I didn't bother with, just because it's more obvious, and that's 1 and 12. Right? You can always take the number 1 and multiply it by the number itself. Okay, so all the factors of 12, and here I'm going to go in order. So the number 1, the number 2, the number 3, the number 4, and the number 6, and the number 12 are all factors of 12. All of these multiply by something to give us 12. And what's kind of cool is you could see that they actually kind of pair up, right? Like that, in order like that. Okay, so if you're interested in listing factors of a number, let's try one more. Let's do the factors. Let's see, list. We'll do an easier, or not necessarily easier, a different one. List the factors of, how about 30? So we want to think about things that multiply to be 30, okay? Well, we know 1 definitely multiplies by 30, so 1 is a factor. 2 goes into 30, we know that, okay? 3 also goes into 30. 4 doesn't work. 5 does, and 6. And at this point, what I'm now seeing is these two multiply to be 30. So the next pair that multiplies to be 30 would be paired up with the 3. So what multiplies by 3 to be 30? 10. And now what multiplies by 2 to be 30? 15. And then last, the 1 will give us 30. And there you go, the factors of 30. Now, the factors that we tend to be more interested in are prime factors. So if I asked you to prime factor 12, we'll go back to 12. I'm asking you to write it as a multiplication of primes, right? As a multiplication of primes. Okay, so we know that 12 is 3 times 4. 3 times 4, or 2 times 6, however you want to think about that. But both 6 and 4 are not primes. So I could kind of think of breaking those up further. In other words, 2 times 2 times 3 would be the prime factorization of 12. Because when we multiply those all together, it gives us 12. And all 3 of those numbers are primes. Okay, so let's look at ways we can prime factor. The book lists 3 methods. And I really think 2 of them are more important. So I'm going to focus on 2 of them, and then I'll mention the third one just so you're aware. The first one is called increasing primes. Oh, here, I'll put a number 1 for first. So this uses the idea that we start with the smallest prime and work our way up until we figure out all the prime numbers that go into our number. In other words, we're dividing over and over again by primes to do that. So here, let me give an example of 300. I'm going to show you how I could factor 300 using increasing primes. So I'm going to start with 2, and I'm going to do a division. And the way I'm going to do the division is I'm going to actually do it upside down. So normally we would do 2 into 300, right? Like that. But I'm going to reverse that. And I'm going to do 2 into 300 like this. Okay. So 2 goes into 300 and gives me 150. And then I'm going to divide by 2 again. So 2 goes into 150 and gives me 75. Okay. And now I know 2 doesn't go into 75. So I would switch to 3. I'm like, okay, so 3 does go into 75 25 times. Now 3 doesn't go into 25, so I switch to 5 would be the next prime number. And that would give me 5, which is a prime. And there we are, I'm done. So the prime factorization is 2 times 2 times 3 times 5 times 5. And if you want to write it shorthand using exponents, you could write, because there's 2 2's, you could write 2 squared times 3. And since there's 2 5's, you would write 5 squared. So either of these are perfectly good for me for prime factoring, whichever form you choose to write it in. So that's the increasing primes method. The other really popular method, probably even more popular, is factor trees. So a factor tree has you start with the number. So we're going to do 300 again. And think of 2 numbers that multiply to be 300. You could do 30 and 10 or 3 and 100, something like that. I'll do 30 and 10. And then you say, okay, 2 numbers that multiply to be 30, 5 and 6. Now 5 is a prime. 6, however, is not. I can actually break 6 up further into 2 and 3, and those are both primes. I'm circling the prime numbers just so I know I'm done. 10 is not a prime, so it's 2 times 5, but both of those are primes, so there we are. And you'll see that we get the same numbers. Now you could write them in different order. 5 times 2 times 3 times 2 times 5. That's not in ascending order, right? I'm just kind of listing them all down. Or again, you can write it in the orders we did above, where we put it in smallest to biggest or with exponents. Okay. The other approach is called the 2 factors approach. I'll call it the bonus. And honestly, the 2 factors approach is very reminiscent of the factor tree. In other words, rather though than writing a tree, they just keep breaking up the 2 factors into 2 more factors. So rather than doing the tree version, they do it linearly. So I'll write it, but I don't want you to get worried about it. So you'd start with, okay, so 330 is, sorry, 300 is 30 times 10. There we go. I can talk. And then 30 is 5 times 6. 10 is 5 times 2. See, I'm breaking 2 factors every time. Okay, this time it was for 30 and 10. Okay, and then I'm like, oh, 6 can break up into 2 factors again. 6 is 3 times 2 and 5 times 2. And there you go. You get the same thing. So it's just doing it linearly rather than as a factor tree. Honestly, I don't care which one you use, but the factor tree approach is probably the most common, most popular among students. There's something very appealing about the factor tree and easier to remember. Okay, Now, before we continue, we've actually kind of just hit on something called the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. And that is that every composite number, whole composite number, every whole composite number, that's an O. Sorry, I'm having trouble with that O right there because there's something on the screen. There we go. Every whole composite number, there we go, can be expressed as a unique product of primes. Of prime numbers, I should say. Sorry, it like would not write. So I just kept going and hoping it would catch up with me. It did. So we can take any composite number and write it as a product of primes. And it's a unique thing. It'll always come out the same. You can reorder it, but it'll always have the same numbers every single time. That's the fundamental theorem of arithmetic. All right, let's go ahead and I want to try another factor tree just because I want to make sure we feel comfortable with that. Let's factor, oops. Actually, if you want to use the increasing primes, you can. But let's go ahead and factor or prime factor 924. All right. If you want to pause the video and give that a try, go for it. I'm going to go ahead and use the factor tree approach. All right, so let's see. Well, I know 2 goes into 924. So I'm going to grab my calculator and I get 2 times 462. Okay, 2 definitely goes into 462, which will give me 231. All right, now I happen to know that's divisible by 3 from last section, because if I add 231 up, that's 6, and that's divisible by 3. So 3 goes into this one. 77 times. Oh, okay, and then 7 times 11. And there we are. I kind of used the increasing primes approach with the numbers I chose specifically, but it doesn't really matter. You could have started somewhere else. You could have started with the number 3 and figured out what that is into 924. Okay. Or you could start with the number 4. 4 goes into 924 since 4 goes into 24, right? You look at the last 2 digits when we're testing to see if 4 works. Okay, so there was a few places you could have started with that one. All right. So let's go ahead and finally talk about greatest common factor. So now we're ready to actually talk about it. The greatest common factor, also known as GCF. So a common factor in general would be a factor that 2 numbers have in common, or 2 different numbers have in common, right? So note a common factor is a factor 2 different numbers have in common. And I got lazy and abbreviated different. I don't know why I didn't put a capital. That's weird. And I don't know why my U looks kind of weird and floating. There we go. All right. Let's do an example of that. Let's look for common factors for the numbers 24 and 36. Okay. So it'd be really smart to probably go ahead and first find the prime factors for 24 and 36, and then use that to kind of help me find what's common. Actually, not prime factors. I'm sorry, just listing the factors of 24 and 36. So, okay, let's start with 24. The factors of 24. And this is back to what we were doing earlier. Okay. So 1 goes into 24. So does 2 and 3 and 4, not 5. 6 does. And now I see that 4 and 6, right? There's my pair. Pairing those two up. 4 and 6 pair up. So then the next number would be what pairs up with 3. That would be 8. Pairs up with 2. That would be 12. And then pairs up with 1 is 24. Okay. Now let's look at the factors of 36. Starting with 1, 2, 3, 4, not 5, but 6. Okay, but 6 times 6 is 36, right? So at this point, I'm going to go with the 4. So this is kind of like its own pairing. I'm not going to list 6 twice. And then 4 times 9 is 36. So then 3 times, well, that would be 12, would be 36. 2 times 18 is 36. And then 1 times 36. Okay, so now I want to look for the common factors. So common factors would be 1, 2, 3, 4, 6, and 12. Those would be the factors they have in common. Now, if I asked you for the greatest common factor, you would say 12. Oops, wow, that was a terrible circle. Let me fix it. Haha, okay. That would be the greatest common factor. Okay, so I think we just kind of defined what that is, but I do want to write the formal definition just so that you have that. So, definition for any two non-zero whole numbers, which we'll call A and B. Sorry, I got mad because I moved the screen and then tried to write pretty quickly after that. A and B, the greatest common factor. Or GCF, which will actually write it. There's like a nice little notation for it. You would use that GCF, and then you actually can indicate the two numbers you're referring to. So in this case, we're doing it in general. So A and B is the greatest factor or divisor. They put that in parentheses, divisor of both A and B. All right, so that's how we define greatest common factor. Now, it was an opportunity to also write that notation, the GCF notation, and how you can do that. I mentioned that one way you could find the greatest common factor, though I didn't do it like that, was looking at prime factors. So I want to actually take that approach rather than listing all the factors out, especially when we start maybe talking about larger numbers. We don't maybe necessarily want to list out all the factors. That might take a while. So doing the prime factorization, it can possibly be quicker. Let's try this. And here we're going to use the notation. Use factor trees. To find, and here we'll do part A and B. So part A will be the GCF of 60 and 72. Okay, so what I want to do is I want to actually prime factor 60 and then prime factor 72. Okay, so let's do that first. So 60 is 6 times 10. And you can start anywhere. In fact, if you want to pause the video and do it, go ahead, do it. 2 times 3, 2 times 5. All right, so there's the prime factor for 60. And here, I'm going to list it in order down below. So 60 is 2 two twos. So 1, 2, another 2. No exponents this time. 2 times 2, and then 3 and 5. Okay. And then for 72, okay, 8 and 9 give me 72. 8 is 2 times 4. 4 is 2 times 2. 9 is 3 times 3. Okay, so 72 is 3 twos, 2 times 2 times 2, and then 2 threes. Okay, so now that I've got those prime factored, I'm going to line up the factors that they do have in common. So for 60, it was 2 times 2 times 3. But I'm going to skip a little, give a little bit of space here and put the times 3 over here. And then I'm going to give a little more space and put the times 5 over here. Actually, here they kind of put the pairing of the X with the number here. Okay. A little space. Okay, and the reason is underneath it, I'm going to write 72, and I'm going to line up what they have in common going in order. So 72 has 2 times 2, but then it has an extra times 2. That's what that space above was for, because there was 3 2s. Then it has 2 3s. So again, the 3s are lining up, but there's an extra 3. And then the 60 has that 5. Okay, so for GCF, we're lining up what they have in common. So they have 2 2s and a 3. And that is the GCF. So the GCF of 60 and 72 is 12, because 2 times 2 times 3 is 12. So 12 would be the answer. Okay, let's try that again now that we kind of know how we're going to do it. The real trick is doing this lining up bit right here, where we line up the common factors, and we kind of have to leave space once we kind of see how many factors the other term has. And we're going to use this method also for least common multiple, like this kind of lining up thing. So it's worth taking the time to feel good about that. Let's try another one, like I said. Oh, sorry, this will be part B of my example. So now I'd like to find the GCF of 180, comma 220. So I would pause, go ahead, prime factor 180 and 220 and see if we get the same things. Okay. So for me, I'm going to start with 18 times 10. Well, it's taking its sweet time. There we go. 18 times 10. Okay. 18, 2 times 9. 9 is 3 times 3. 10, 2 times 5. Cool. 220. 22 times 10. That's 2 times 11. 2 times 5. Okay. So it looks like this first number, 180, has quite a few smaller numbers. Let's see. We have 2 2s. And then we have 2 3s. The other one doesn't have more than 2 2s, so I don't have to worry about any spaces there. And then it has a 5. Okay. 220, I'm going to line up, has 2 2s as well. Then it has a 5, and then it has an 11, which I just put at the end. No real space there, but for some reason it does not want to draw my X's. There we go. Okay. So now I'm going to line up what factors they have in common. In this, they have 2 2s in common and a 5. So 2 times 2 times 5, which multiplies out to 20. And there you go, the GCF. Okay, now, I don't want to do a separate video for LCM because it's not going to take that long because we kind of just set up ourselves for doing the LCM. which is the least common multiple. Sorry, I don't know why I keep calling it by the acronym without having introduced that yet. The least common multiple. Before we talk about the least common multiple, let's talk about multiples. And the book doesn't really define it. It just kind of jumps right into it and says there are an infinite number of multiples for a number. There are an infinite number of multiples. Sorry, of multiples. Wow, that's not how you spell multiples. For example, if they were to ask you to list the first 15, list 15 multiples. Here, I'm going to do two different numbers because, wow, this computer is getting so annoying. Multiples. And that does not look like a freaking T. It looks like a 7. There we go. List 15 multiples of, and the first number I want to do this for is the number 5. Multiples of 5 are things that 5 multiplies by to be that number. Okay, so the first multiple of 5 is itself. This is a part A, by the way. Sorry, that looks kind of weird to me in my head. I kind of looked at that and was like, that doesn't look much like a parenthesis. Wow, this computer is lagging so bad because I'm trying to do one lesson of this and it's just not wanting to keep up. Okay, so 5, 10, 15. Wow, that's your 10, huh, computer? 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75. So much fun. Okay, that's the first 15 multiples of 5. All right, numbers that when you multiply 5 times that number, it gives you those. So like 60 is a multiple of 5 because 5 times 12 is 60. Okay, and so forth. All right, I'd like you to try this now. For 7, I want you to list the first 15 multiples of 7. So part B will be 7. And if you need your calculator, that's completely reasonable. Okay, let's see. 7, 14, 21, 28, 45, 42, 49, 56. Sorry, lost my train of thought there. 63, 70, 77, 84. And now here's where I needed my calculator. 91, 98, and wow, that's an 8. And 105. Well, I could actually just keep adding 7 every time and get them, but still. All right, there we go. So there are the first 15 multiples of 7. So if I wanted to find common multiples, I'm looking for multiples that are both multiples of 5 and 7. So let's do that. Let's say I'd like to find common multiples for 5 and 7. This will be part C. List some common multiples. Sorry. It really is upset. And I'm having to write very, very difficultly here. Okay, so for 5 and 7, let's see. Well, definitely 35 and 70. Those are common multiples for these. And now, as you can guess, if I kept going, there would be more. But the idea with least common multiple is I'm interested in the smallest of them. And the smallest of them would be 35. So this would be the least common multiple. I'm going to abbreviate multiple since the computer's having such trouble. And that is the word least, even though it's kind of badly spelled. I'm sorry, just computer is struggling and I'm tired of erasing over and over again. And now it doesn't want to move. There we go. All right. Okay, let me define LCM just like I did the GCF, and then we'll do some examples and I'll show you how we're going to use the factor trees to do the LCM. So definition for any two non-zero whole numbers, A and B, numbers, it's so struggling, A and B, it just does not want to cooperate. There we go. The least common multiple which also has a special notation written. Go ahead and shift that up. The LCM of A and B is the smallest multiple of both A and B. Is the smallest multiple A and B. All right. Okay. If it lets me fix this D, life will be better. There we go. Let's try an example. As I said, we're going to use the same kind of approach with factor trees to start. All right. So use factor trees. And we're going to do the lining up thing for the factors. It's so slow. I'm so sorry. Use factor trees. There we go. And for the LCM of, let's do 40 and 66. So go ahead and prime factor 40 and 66. Pause the video, prime factor them. Make sure you match what I get. So I'm going to do 4 times 10. 4 is 2 times 2. 10 is 2 times 5. 66 is 6 times 11. 11's done. That's a prime. So 6 is 2 times 3. Okay, so I'm gonna start by writing the factor for 40, but I have to be careful. So I have 3 2's, but then the other one has a 3. So I'm gonna put a space for the 3 and then put the times 5. Okay, so then for 66, I have a 2, and then in that blank space there, I'll put the times 3, and then after the times 11. Okay, now here's what's different for the LCM. For the LCM, we don't write what's in common now. We actually line them up and bring everything down into the LCM. So for this one, we're going to have 2 for the first column, 2 times 2. So oops, sorry. Wow, that's supposed to be another 2. So basically, everything is coming down this time. Every column is coming down. So that's a sad looking times 2 right there. Let me see if I can fix it. If it will let me. It's so mad at me. I'm writing so much. It's having trouble. Times 3 times 5 times 11. Okay. So get your calculator. Multiply those numbers together. And that's going to give you the LCM for 40 and 66. And what I got was 1320. Big number. That's the first number these two have in common. That's kind of amazing when you think about it. that it takes that long before we can actually see an LCM. But there you go. That's the least common multiple. Let's try another one. So this will be part B. Let's find the LCM for 28 and 44. Okay, pause the video, prime factor, please, and see what you get. I'm going to start with prime factoring 28. So 28 is 4 times 7. And then 7's done. So 4 is 2 times 2. Cool. All right. And then 44 is 4 times 11. 11's done. And again, 2 times 2. Okay, this one's a little more boring, I think, compared to the last one. All right. So 28 is 2 2s and then a 7. And I can actually write that just in that order because 11 will go after the 7. So 2 times 2 times 7. All right, let me shift up my screen here. Okay, so then for 44, we have 2 times 2, and now I'll skip and put the times 11. Okay, and now I'm going to bring all the numbers down here. So let's see. I am getting 2 times 2 times 7 times 11, which I actually don't know off the top of my head. I didn't write the answer for this one. So here, let me grab my calculator and we're going to plug it in. I'm getting 308. Here, I'll actually just put it up here since it's already written at the top. And there you go. That's how we find the least common multiple.